So don't worry, it's playing. It will start now.
So hi everyone, welcome to the last session of the workshop. I'm Alex. I'm going to be talking you through our lesson on machine learning and using Mapminer. So before I kind of get into the coding, I just want to show you a little summary diagram overview of what we're going to be discussing today. So I'm going to be introducing a few packages that we've developed for doing machine learning of material science data sets. So the main one of these is called Mapminer, and it links data retrieval tools. I'll go into what that means in a minute, with methods for generating machine learnable descriptors, and also visualization packages, and then tying all of these together with machine learning packages, which we didn't develop these machine learning packages. They're kind of very well known. And these are things like scikit-learn. Okay, so I'm going to go back to my blank notebook. So I said that Mapminer kind of links these data retrieval tools. So it interfaces with a series of materials databases. So these are things like the Materials Project, Citrine, AFlow, and there's more. But it also includes over 30 data sets that have been taken from the published literature. And so these are data sets which are ready to be used straight away. And so we can actually look at what data sets are available in Mapminer by using this get available datasets function. So let's go ahead and import that. So it's from Mapminer, and then all of these data sets are in the datasets module. And then we can import get available datasets. And once we've imported this, it might take a second. We can then just run that function, get available datasets. And when we run it, it's scrolled me all the way down to the bottom. If I scroll up, this prints out a list of all the available datasets in Mapminer and a short description of what those datasets contain. So for example, we have this Bolt-Trap MP dataset here. This is the identifier. And you can see it contains effective mass and thermoelectric data of 8,000 compounds taken from the Materials Project. So let's come down. Let's find a data set that we can load. So I'm going to take, I'm going to use the dielectric constant data set, and we're actually going to load that in. So we can do that in a new cell down here. And so to load data sets, we need to use the load dataset function. So that is accessible from Mapminer.datasets, and then we're going to import load dataset. So let's import that. And then we can load our dataset into a variable called df. If we type df equals load underscore dataset, and then our dataset name is going to be called dielectric underscore constant. And we also need to add a little bit extra here. We're going to add data home equals open quotations dot. And that's just a quirk of CoCalc, which means that we have to download the data set to the current directory. So if we shift enter, you'll see here that it's fetching this dielectric constant data set. That's because we don't actually include all the data sets in Mapminer to kind of keep the repository size down. And instead we upload them all onto Figshare. And so the first time you ever try and load it, it will download it from the internet.
Everybody installs Mapminer, and once it's installed, we're going to do exactly what he does. Okay.
Okay. So I paused the video because then some people, I mean, we can't see exactly everything.
I mean, there's no need that everybody does it, but please download Mapminer and install it.
Yeah. So please bear with us. We'll brainstorm the best thing to do just now.
Down to the bottom, if I scroll up, this prints out a list of all the available data sets in Mapminer and a short description of what those data sets contain. So for example, we have this Bootstrap MP data set here. This is the identifier. And you can see it contains effective mass and thermoelectric data of 8,000 compounds taken from the materials project. So let's come down. Let's find a data set that we can load. So I'm going to use the dielectric constant data set, and we're actually going to load that in. So we can do that in a new cell down here. And so to load data sets, we need to use the load data set function. So that is accessible from Mapminer.datasets, and then we're going to import load dataset. So let's import that. And then we can load our dataset into a variable called df. If we type df equals load underscore dataset, and then our dataset name is called dielectric underscore constant. And we also need to add a little bit extra here. We're going to add data home equals open quotation.
Take a bit of time when people are installing Mapminer. There's a number of people installing Mapminer.
So it's important for you to install Mapminer. So I think you do pip install. So you open your Jupyter, and if you do pip install Mapminer, and then shift enter, you should be able to install it. But I think he's going to say that he has to install PyMyGen before, and then it will install the PyMyGen for you. Okay? It will install everything it needs. So just open your Jupyter, exclamation point, pip install Matminer, and then it will install Matminer, but on the way it needs to install PyMyGen, so it will install PyMyGen for you. Okay? So if you do that, then you will be able to follow better all of this. Okay. So I think everybody is clear. You put an exclamation point in your Jupyter, pip install Mapminer, and then once you do that, you should be able to, it will install Mapminer and PyMyGen that you need, and then you should be able to follow on. Okay. So we'll continue.
Dot. And that's just a quirk of CoCalc, which means that
It's still installing it here.
Oh. Okay.
I think there's no one who has a fully working version of Mapminer at this stage. Some are advancing, but everyone I think is advancing, but it takes time.
Okay. So while your Mapminer is installing, you can watch what he's doing and have a.
we have to download the data set to the current directory. So if we shift enter, you'll see here that it's fetching this dielectric constant data set. That's because we don't actually include all the data sets in Mapminer to kind of keep the repository size down. And instead we upload them all onto Figshare. And so the first time you ever try and load it, it will download it from the internet. So all the data sets that are available in Mapminer are pandas data frame objects. So we had a nice introduction to those earlier. Oh, I'll just increase my font size a little bit. Hopefully this will make it more visible. So yeah, we had a nice introduction to those earlier from Rachel. So you can think of these data frame objects like Excel spreadsheets, except for I'd say they're a lot more powerful than Excel spreadsheets. They make modifying and searching through your data much easier. So we can have a summary of what's available in this data set by using the head function. So if we type df.head and then scroll up a little bit, you can see we have a kind of spreadsheet here where we have columns along the top and then our rows along the side. So in our data frame, we have things like the material ID, which are the identifier number from materials project, the volume, the structure object, and then the dielectric constant information here. So this is E electronic and E total. So you can see that if there's many columns, you might actually have to scroll across in order to see them all. And sometimes actually, if there's too many columns, they'll kind of get summarized by an ellipsis. And so you can actually just print all the columns that are in there using the columns attributes. So that's df.columns. And here you can see this is a list of all the columns in the data set. One nice thing about data frame objects is they have a describe function, which gives us a summary of all the numerical data in the data set. So if we type df.describe, you can see here it gives us some statistics about all the different columns in the data set. So things like the min and max and the standard deviations. So you can index data frames in a similar way that you would index a dictionary. So for example, if you wanted to select a column, so let's say we want to select the band gap column, we can do df, open square brackets, band gap. And then if we shift enter, you can see here, we've got a list of all the band gaps for each row in our data set. And this is what's called a series object's been returned. We can actually call the values attribute of this, and this returns a NumPy array of these different values. So we can also index the data set on rows instead of columns. And for that, we use the iloc command. So that it would be df.iloc, and then we put in a number here. So for example, 100 would give us the 100th row, or it's actually the 101th row. And then here you can see just a summary of all the properties associated with that row. So data frames are really nice because we can use these indexing tools to filter them really effectively. So let's say we wanted to filter our data set to only include those with a volume greater than 580. So the first thing we do is we create what's called a Boolean mask. And this is just a series of true or false. So let me show you. If we do df volume, that's going to select the volume data. And then we're going to ask for all of the volumes that are greater than or equal to 580. And here you can use any Python comparators when you're filtering the data frame in this way. And you can see that we get returned a list of false or true, depending on whether the volume matches this criteria. So what I'm going to do is I'm going to store this line in a variable called mask. So this is our Boolean mask. And then I'm going to index the data frame using that mask. And you can see when I do this that now there's only 4 rows and all of them have volumes above 580. So you can see we've got a lot of extra columns here. Once we've loaded a data set, we might realize that we don't want all of them. And so we can drop the columns that we don't want using the drop command. So for example, here, I'm going to create a new data frame called cleaned data frame. I'm going to put equals df.drop, and then I'm going to drop the n sites column and the space group column. And when we use the drop command like this, we have to specify whether we're dropping columns or rows. And to do that, we use the axis option. So here I'm going to put comma axis equals 1. So this means we're dropping columns, and if this was 0, that would mean we were dropping rows. So if I do that, and then let's have a look at our clean data frame here, cleaned data frame, and we can run the head command on that. You can see that now we've got a data frame missing the n sites in the space group columns. So the last thing I want to introduce to you, which again is really useful when you're doing data analysis, is the ability to create new columns. So much like you can use the Python comparator kind of functionality like equals or greater than equals to, you can also use the Python math operators as well. So these are things like plus, minus, and times. And so let's say we want to create a new column in this data frame. So let me scroll up and show you what we have in here. We've got the polyelectronic, polytotal, and these are the dielectric constants for polycrystalline samples, the total and electronic contributions. Let's say we wanted to get the contributions from just contributed from the ionic motion of the atoms. So we could create a new column in our data frame called polyionic. So we index the data frame for polyionic. This doesn't exist yet, but we're going to create it. And then into polyionic, we're going to add, we're going to calculate it based on the polytotal and the polyelectronic. So here we're going to say equals df polytotal minus df polyelectronic. And if we run that and then have a look at our data frame again, we can see if we scroll all the way across to the far most right, that we have a new column in our data set called polyionic. Okay, so that's just a very quick introduction into how you can manipulate pandas data frames. There's an exercise associated with this first lesson. If we go back to the files directory, and then if you navigate to this unit 1 exercises here, I'm going to give you all 10 minutes or so to have a go at employing some of these techniques that I've just introduced on some other data sets from Mapminer. So you've got 10 minutes. I'd say you can all have maybe 7 or so minutes to do it, and then I'll go through the answers for the remaining three minutes. Okay, I think I'll go through how I would have tackled some of these exercises then. So this first exercise wanted you to load and examine the Elastic Tensor 2015 dataset. And so we can do that, as is the hint here, using this load dataset function. So what we need to do here is just ask for the dataset using the identifier, and the identifier is just the name Elastic Tensor 2015. And so if we put the identifier in here and run this cell, this will download the dataset from the internet and then initialize it into this data frame variable. So we then wanted to find out the largest value of bulk modulus in the dataset, and the bulk modulus is given in this KVRH column. And so we can get that by running the describe function on the data set. So if I just do df.describe, and then we come across to the KVRH, and the maximum value is given in this bottommost row, and so the maximum value is this 435 there. In the second exercise, you are asked to filter the data set based on a certain number of sites. So we can do that using the indexing behavior that I showed. So here we can do data frame. The first thing that we do is create a Boolean mask. So we make our mask like this. We then filter on the number of sites. So n sites is less than 20. And we create a new data set called filtered data frame equals, and then we index the data frame using the mask. So if we run this, that should only take a second. We can then look at the number of materials if we wanted, just using the len command. So we can say len filtered data frame, and that gives us 975. And we can get the mean number of sites using the mean command of pandas data frames. So we can say filter df, ask for the n sites column, and then call the mean function on that. And you can see here the mean number of sites is 8.55. And then the last exercise was to remove columns which are unnecessary for machine learning. And so this is a very common thing that you'll have to do. And again, we can do this using the drop function. So here we're asked to remove all the sites so that it only contains formula structure KVRH. So let's first of all see what the rest of the columns are. So you can see we've got material ID formula, all of these. So one thing that you could do would be to use the drop command. So you would type df.drop. We can put the things that we want to drop in here. So for example, material ID, n sites, and then etc. with all of these. And then you can do, you need to specify that we want to drop columns. So we ask for axis equals 1. So that's one way of dropping these sites. The other way is actually we can index, and this is a bit of cheeky because I didn't actually show you how to do this, but we can index the data frame just asking for the site for the columns that we want. So the columns that I asked you to get there were formula structure and KVRH. So here we could say, let's make a new function, a new variable called toKeep. We're going to make this a list of these 3 columns. So this is formula, structure, and KVRH. We can then index the data frame using this toKeep variable, like that. And you can see that now our data frame only has that columns. So this is a really useful way of filtering your data frame if it has a lot of columns to begin with. Okay, so I'm going to go back to the blank notebook that we created, and we're going to continue with the second lesson. So firstly, I just want to show you another image, another summary image of what we're going to be covering. So, maybe I'll have to zoom out a little bit just to show you for a second. So in the second section, I'm going to show you how we can generate machine learnable descriptors that we can then actually feed into machine learning algorithms. And so the idea here is that so far throughout this workshop, you've been using these material science primitives, we would call them. So these are things like composition objects, structure objects, band structures, and density of states. But the machine learning algorithms that we want to use, they don't understand these kind of objects. So instead, what we have to do is convert them into raw numerical features, or that the machine learning algorithm will actually understand and be able to learn from. And so a large part of Mapminer is implementing tools to do this conversion. And so I'm going to use some terminology here. We call the things that you learn in machine learning features. And you can think of these just as vectors of numbers. we call the process of turning compositions and these objects into features featurization. And the classes in Mapminer that do this conversion, we call featurizers. Okay, so how do we use some of these featurizers? So let's make a new cell here. We need to first create an object that we can featurize. So let's, for example, use a composition object. So we're going to make a composition. So to do that, we import the composition class from PyMatGen. So we're going to type from PyMatGen import composition. We're going to create a new composition for iron oxide. So here we're going to type Fe2O3 is equal to composition, and then we're going to put Fe2O3 as our composition there. So this is a PyMatGen composition object. We can then featurize that using the Mapminer featurizers. So all of the featurizers in Mapminer are in the featurizers submodule. So we can import one by going to from Mapminer.featurizers. And then here we want to select a composition featurizer. So we type dot composition. And I'm going to demonstrate how to use the element fraction featurizer. So I'm going to type import element fraction. And we can initialize this featurizer in a typical way that you would initialize any class. So we're going to just call it EF, and we're going to say EF equals element fraction, and then parentheses like that. So one thing I'll note is that here you see I'm importing this composition featurizer. For other featurizers which are based on different PyMatGen objects, like structures, for example, they would be in a different module, so they would be in the structure module. Or if it's a band structure, that would be in the band structure module. So all the featurizers available in Mapminer implement the featurize function. And this does that conversion that I was telling you about before. It takes in a primitive object and gives out a vector of numbers. So let's use this featurizer that we've just initialized. I'm going to create a new variable called element fractions. And this is going to contain our features. And then into that variable, I'm going to put the features using ef.featurize, and then we're going to give it our composition object. So if we examine what's in this variable, just by putting it in there and doing Shift Enter, you can see that it's basically a whole string of zeros, and then a couple of other entries. We've got a 0.6 and a 0.4. So what does this all mean? Well, these featurizers also implement a function called feature labels, and this tells us the title of each of these features. So each of these numbers is a separate feature. So we can type ef.featurelabels, and you can see that each of these is a different element. So this class is called element fraction. You may have worked out that these numbers are the fraction of that element in the composition. So how can we verify this? So if we type element, so let's have a look at the 8th element, which we know is oxygen. So we're going to index our element fractions, which we just created to get the 8th one. So we'll type element fractions 7. I spelled that wrong. And you can see it gives us 0.6, or this means that oxygen makes up 60% of the composition. And we can verify that this is oxygen by using those feature labels that I just showed you. So we can type ef.featurelabels and then look at the 7th or the 8th one there, and you can see that corresponds to oxygen. Okay, so here I've just shown you how to generate features for one composition. In general, you're going to be dealing with data frames, and these data frames are going to be containing many different compositions simultaneously. The nice thing about these featurizers is that they have utility functions for generating features for a whole data frame of particular objects. And so all these featurizers implement the featurized data frame function. So let's try it using this element fraction featurizer. The first thing we're going to do is load a data set. So let's do that now. I'm going to import that load dataset function. In fact, I think everyone should already have it loaded, but I'll import it again in case. So from Mapminer.datasets, import load dataset. And then I'm going to import the Brgosh super hard training dataset. So I'm going to type df equals load dataset, Brgosh super hard underscore training. And then again, we need to tell it to install to the current directory. So for that, we're going to type data home equals and then dots like that. So that's downloading that data set now. Once that's done, we can just have a look at what's in our data set. So you can see we've got a formula column, bulk modulus, and if we come across, we have a composition column here. So this contains a composition object for each row in the data set. So now we can use this featurized data frame function, which I just mentioned, to generate these element fraction features for every row in the data set. So to do that, I'm going to type df equals ef.featurize data frame. So in each case, all the featurized data frame functions for every featurizer follows the same format. The first argument is the data frame that you want to featurize, and the second argument is the column which contains the object that you want to featurize. So here we're featurizing compositions, so we're going to give it the composition column, and we can just put composition in quotes like this. And you'll get a fancy progress bar, and that was really quick. If we look at our data frame again using the head function and shift enter, and then scroll across, you can see that now we have all of these elemental columns correspond to the fraction that that element makes up of the composition. So here you can see that I featurized the composition column. If, for example, you were featurizing structures rather than compositions, you would need to give the column which contains structures rather than compositions. So in this case, it would be the structure column. So there's one last special case of featurizers that I want to introduce, and those are conversion featurizers. So first, to show you why they're important, I'm going to load a different data set. So this data set is called phonon dielectric underscore MP. So I'm going to load that now. Load data set phonon underscore dielectric underscore MP. I'm going to tell it to download in the current directory. So that's data underscore home equals dot. It's going to download this, and then let's examine this data frame. So here you can see there's not many columns. We have a structure and we have a formula, but we don't have a composition column. So if we wanted to generate composition-based features, we would first need to generate a composition column that we can featurize. So you think, okay, the formula is very close to the composition. Why can't we use that? Well, you see, the formula here is a string object. It's not a composition object. So what we want to do is actually convert this string into a composition object. And that's why I have these conversion featurizers, just to make this sort of procedure very simple. So I'm going to import the conversion featurizer that can do this. And it's very obviously named string to composition. So the conversion featurizers live in mapminer.featurizers.conversions. So I'm going to import that now from mapminer.featurizers.conversions, import string, capital S, to capital T, composition. We can initialize this featurizer like we would any other. So I'm going to call this one stc equals string to composition. And then we can featurize the data frame to do this conversion in the same way that we featurize the data frame to generate composition features. So we can type df equals stc.featurize data frame. The first argument is the data frame that we want to featurize. The second argument is the column, which contains the object that we want to featurize. And in this case, it is the formula. So it's the formula column. And if we do this, this is really quick. We can then look at our data frame and see, if we scroll all the way across to the end, that now we have an additional composition column. So that's a very quick introduction into generating features. There's an exercise for you all to do now where you'll be generating some composition features, some structural features, and also using these composition featurizers. So this is in the files and it's called Unit 2 exercises here. So again, I'll give you 5 or 6 minutes to have a go at these and then I'll go through the answers. So I just want to respond to a question which was asked in the Slack. And that is, how powerful are these weight fractional features that I just mentioned? So can they describe all kinds of properties, or do they perform well on target properties? So the thing which I definitely should have mentioned is that that was just one example of one of the more basic features that we have implemented in Mapminer. Mapminer actually includes thousands of different features based on featurizing many different objects. There's a summary that you can see of all the different featurizers available in Mapminer. If you go onto, if you just search for Mapminer features or featurizers, there's a link to this table of featurizers here, which gives a summary of all the different featurizers that are available. So for example, under composition features, we have ones based on different element properties, such as the ionization potential of that element. We've got things based on the oxidation states. So for example, ionic radii and things like that. And as you can imagine, different features are going to be different, are going to be beneficial for different problems. So if you have something, if you have a property which is very dependent on anisotropy, then a compositional feature is probably not going to be very good. You'll need to have something which can encode structural information as well. And so you might want to use some of the structure featurizers that we have available. So these are things like the dimensionality, which will encode the dimensionality of your structure and things like that. So coming back to, oh yeah, and the last thing I should mention is that there's no real guaranteed way of working out in advance which features are going to be best. And so generally what you have to do is try out a whole host of different features and see which is working for you. And that's actually something that we'll come on to a little later. So let's return to these Unit 2 exercises. I asked you to load a data set to start with. This is actually a useful time to introduce this load data frame from JSON function. This is a very convenient way to load and save pandas data frame objects in JSON format. So you can see it's been loaded from utils.io. There's a load data frame from JSON, and there's also a dump data frame from to JSON, which saves it to file. So let's load it. So the first thing you're asked to do was use the conversion featurizers to convert a formula to PyMatGen composition. So here you need to fill in the blanks. So as I've mentioned, the first argument of these featurized data frame functions is your data frame, and the second argument is the column that we want to featurize. And in that case, it's the formula column we were told here. So we can put formula in there. We're then going to ask to put in some composition features. So here we're adding the element fraction features, and we want to add them to the composition column. So we can replace this with composition. And then in the last example, you're going to add some density features. And so again, the first argument is the data frame. And then now we want to put featurize the structure objects. So we can put the structure column here. And this might take a little bit longer, but it still should be pretty quick. Okay, so now we can go on to section 3. So in section 3, I'm going to demonstrate how you can actually use these features to do machine learning. So for this part of, let me just reopen my blank notebook. Here we go. So for this part of the exercise, we're going to be using a package called scikit-learn. So this is an open source Python package for machine learning. And we've really designed Mapminer to try and operate with scikit-learn as efficiently as possible. So what we're going to do is load a data set where I've already added a lot of features which you can use for machine learning. So here's one I prepared earlier. We're going to load this data frame using that load data frame from Json function that I just mentioned. So that's present in, so we'll type from mapminer.utils.io import load underscore data frame underscore from underscore JSON. And this data frame is present in the resources folder. So we can load that in by typing df equals load. I'm not going to say all the underscores, but load data frame from JSON. And then it's in parentheses, quotations, resources / elastic. And if we just type LA, it should tab complete. It doesn't want to. That's oh no, I've spelled elastic wrong. Elastic. Here you go. And we can select the one which says featurized at the end. And if we shift enter on this cell, we can now have a look at what this data frame contains. So you can see it has the structure, the formula, this column, which is KVRH, which is the bulk modulus column. So that's going to be our target property and the thing we're trying to machine learn. It has the compositions, and then it has all the features which have been added. So these are called Magpie features. These were added using the element property featurizer. And then we also, I think if you come all the way to the end, we have some density-based features. So we have the density, the volume per atom, and the packing fraction. So the first thing we need to do is separate our data set into the features that we'll use for machine learning and the target property. And each of these has to be based in separate variables, because if you have the target property in the same object as your features for machine learning, then it's going to be a very easy machine learning challenge because it will just learn directly from your target property. So first of all, we're going to select our target property and we're going to call it Y. So we're going to say Y is equal to df. We're going to index the KVRH, so the bulk modulus column, and we're going to ask for the values. So this is just going to be a NumPy array object of the bulk modulus. Next, we're going to separate our machine learnable features into a variable called X. So we're going to say X is equal to, and then we're going to just drop all the columns that we don't want from this data set. So here we don't want structure, formula, KVRH, or composition. So let's type that out. It's going to be df.drop. We have a list here of structure, formula, composition, and KVRH. So you'll notice that we're only keeping these numerical columns because, as I said before, these machine learning algorithms don't know how to learn these structure and composition objects. And the last thing we need to do is select the axis that we want. And because we're selecting columns, we're going to ask for the first axis. So axis equals 1, sorry. And then we can see the features that we have in our X variable by just calling the x.columns attribute. So here you can see this is just a list of all these features that we saw before. So scikit-learn makes it very easy to use these generated features for training machine learning models. So in the interest of time, in this example, we're just going to try out a single machine learning model. But in practice, it's probably best, if you want to get good performance, to try multiple models and see which gives the best performance for your problem. So a very good starting model, which generally can give reasonable performance, is called the random forest approach. So this is an ensemble method, and we can use it by importing it from scikit-learn. So we type from sklearn.ensemble import random forest regressor, where R, F, and R are capitalized. And we will initialize this model into a variable called RF. So we'll say RF equals random forest regressor, and we're going to initialize it with this attribute of n estimators equals 100. So if we run this, that should run very quickly. So this n estimators attribute here, this is an example of a machine learning hyperparameter. So most machine learning models in scikit-learn will contain these hyperparameters, and these will affect the performance of the model, so how accurate the actual final machine learning model is. And so in order to obtain good performance, you not only need to try out different machine learning models, you also need to try out different hyperparameters as well. And similarly, there's no way to really know in advance which hyperparameters are going to be best for your problem. The only way to find out is to try different values and then compare the performance of your model between them. But here we're just going to use n estimators equals 100 because that's a fairly decent value to start with. So we can fit our features to our target property using the fit method. So this is actually going to do the machine learning. So we can type rf.fit. The first variable is our features. The second variable is our target property. And this might take a little bit of time. And you see our CPU shoots up for a second then, but now it's finished. So that's actually trained the full machine learning model. So what we want to do now is evaluate how well it's doing. And so fit trains the machine learning model. We can use the model to predict unseen values by using the predict function. So here we're going to store the predictions for all rows in our data set by typing ypred equals rf.predict, and then we're going to give it our features. So ypred now contains a list of our predictions. So this is the predicted bulk modulus with units of gigapascals. And we can see how close these predictions are to what they should be, to the actual true value, by calculating the error. So scikit-learn includes a few different functions for calculating the error of predictions. So we're going to use the mean squared error function here. So for that, we'll do from sklearn.metrics import mean squared error. And we'll calculate the mean squared error by typing MSE equals mean squared error, and we'll just give it the y values, which is the correct bulk modulus values, and then the predicted values, which is ypred. And we can then take the square root of this mean squared error. And to do that, I'm going to import NumPy, and I'm going to call it NP. This is just a shortcut. So now NumPy is aliased as NP. And I'm going to type NP dot square root, and then this MSE variable here. So you can see we've got a mean squared error of our model of 7.2, which looks very reasonable. But there's an issue here, and I think anybody that's familiar with or has done any machine learning before.
Okay, thank you very much to everybody. So we're going to pause now. We're going to go to the next tutorial. I think we'll have time to watch this video again. We'll send you a link to the video and you can watch it on your own and practice on your own. And also the files we need will be in the link, so you'll be able to practice on your own. Now we have a live person, and that is Dr. Yusuf Shaidu. So, so Yusuf is going to share his screen. And he's going to teach us how to develop potentials using Panel.